Let me show you one more example of finding a function's inverse. We're starting off with a square root function here. Simple enough looking. F of x equals the square root of x plus 3. So this is the square root function shifted 3 units left, which means it would have a domain of -3 to infinity, and a range. Remember, the square root graph starts at the origin and goes upward. If you shift it 3 left, it starts at the point -3x 0 for y and opens upward. So its range would be from 0 in the y direction going to infinity. So remember, this domain and range situation here is going to be very important when you go to the inverse because, well, let me show you. When we go through the process of finding the inverse for this function, this is my original function, y equals the square root of x plus 3. We're supposed to go through the swap to actually create the inverse. So if I swap the x and the y, then I turn this into x equals the square root of y plus 3. And there are only 2 steps involved in solving this for y. I need to square both sides to get rid of the radical, the square root radical. So x squared equals y plus 3, and then subtract 3 from both sides. So when I finally solve this for y, I subtract the 3, I get y equals x squared minus 3, and this technically is the inverse function's formula. F inverse is x squared minus 3, but here's my question. If you go by this and completely forget the construction process that built this, if you're prompted for the domain and range of the inverse, you're going to be in for a few mistakes. See, this inverse appears to be a quadratic. Quadratics are polynomials. They usually have an all real number domain. But because this specific quadratic was created to be the inverse of this square root function, you've got to remember this. And this is of paramount importance because it is a common mistake I've seen some people make in the past. The domain of the inverse function is always going to be the exact same interval notation as the range of the function it came from. So notice, you're not using an all real number domain for this quadratic. You're using bracket 0 to infinity, which means instead of you getting the full parabola shifted down by 3, you're only getting half of the parabola shifted down by 3. Similarly, now this one you probably get right anyway. Since this is a parabola shifted down by 3, it should have a range of -3 to infinity in the y direction, and that is validated by the domain of the function you're starting with. The domain of the original function becomes the range of the inverse, and so they'll always be the same interval notation sets. So I know that when I graph the function f and its inverse on this grid, I've got to make sure that they reflect both of these domain and range sets. So the original function is, again, the square root function shifted 3 clicks left. So that one's pretty straightforward to draw. 3 clicks left, starts at -3, opens upward like the square root shape. There's my f of x. Now this, again, if you didn't do all this analysis, you would think, well, I need a parabola shifted down by 3 and I'm done. Well, yeah, you do need a parabola shifted down by 3, but its domain is only 0 to infinity. It's not all real numbers. So you won't see the left half of the parabola. You'll see the parabola starting at a y-intercept of -3 and then opening upward something like this. See, that's the graph of f inverse, just half of a parabola. And again, when you double check the symmetry, you can see that both the graph of f and its inverse are symmetric with respect to that line, y equals x. So if you turn your graph sideways, you can kind of see that they have that symmetry going for each other. Common mistake whenever you take the inverse of a square root function and you get a quadratic, it's very tempting for some people to think, well, I just graphed the full parabola. But no, if it's created to be the inverse of a square root function, you can only have half the function because of this domain restriction. So be really, really careful about that whenever you're dealing with inverting square root functions. Oh, one more thing I want to show you about graphs is some of the last few problems in your homework, you're prompted just to take a given function and sketch the graph of its inverse? Well, I mean, one thing you can do is you can kind of use that line y equals x symmetry, but be careful. This is the symmetry line, which means you can't just rotate it sideways or do something like that. What you'd actually end up having to do, the best way I guess I can show you how to mimic that symmetry, is if you took a graph of the original function and put it on a post-it note. So there's the x-axis and here's the y-axis. And the original function looks something like this. It's a series of line segments connecting to different points. So there's the original graph of f. What you're trying to do to create the graph of an inverse is you want to swap x and y. You actually want the, I can get the post-it note up. You want the old x-axis to become the new y-axis, and you want the y to become the x. But you also want positive x to correspond to positive y, and you want positive y to correspond to positive x. So again, you can't just rotate it 90 degrees one way or the other. That's insufficient. In order to get the idea of using this symmetry line to get a correct graph of the inverse, what you actually have to do is grab the upper right and lower left corners of your post-it. Works best with a square post-it note. And then flip it diagonally. And then you can kind of see the image of the inverse right there. That's the only way to guarantee that what used to be the y-axis is now the positive x, and what used to be the x is now the positive y. And so this image right here is what the proper inverse should look like. Because you can even see through the post-it note, that diagonal line is still in the same position. It has to keep that same position to go from the function to the inverse. So, I mean, that's one trick on how to create the function's inverse graph. If you're given a graph like this, honestly, the easiest trick is just to take each of the coordinates on each of the points. Like this is the point 3, 4. This is the point 1, 3. This is the coordinate 0, -1, and this is the point -2, -4. Each of these points, these xy coordinates on the original graph, they get reversed to go to the inverse graph. So this point here, 3 for x, 4 for y, should become 4 for x and 3 for y on the inverse. Okay, 4, 3. This one at 1 for x, 3 for y would become 3 for x and 1 for y. 3, 1. This y-intercept of -1 should become an x-intercept of -1 on the inverse, -1, 0. And this last point down here, you're swapping the positions of x and y again. So that means on the inverse, that will be -4 for x, -2 for y. And then they're just a connected series of line segments. It looks something like this when you finally get them connected. But even if I overlap my post-it note graph with this much more accurately drawn graph, if I, here's the original image that I traced, grab the upper right corner, lower left corner, flip it diagonally, you can see there's still a good point-for-point matchup when I overlap my post-it note and the graph that I just made. So either way, it's a handy way to create the inverse. Okay, is to use that symmetry with the line y equals x.